Welcome back, everybody. Section 6.4 is the last section we are going to cover today, March 31st, Tuesday. This is entitled Factoring Special Types of Polynomials. These are going to be the special types. First of all, we're going to show you how to factor what is called the difference between squares. And the difference between squares is this right here. You may remember from the last chapter that the difference between squares is always produced when you multiply conjugate binomials together. So hopefully this rings a bell. You see, back in chapter 5, we went from right to left, though. Now we're going from left to right in chapter 6 and factoring the difference of squares back into the product of their conjugate binomial factors. That's called the difference of squares. Difference between two squares. The sum of squares. The sum of squares is going to be, in general, something that looks like this, a binomial that looks like this. Unfortunately, ladies and gentlemen, the sum of squares can never be factored. So the sum of squares is non-factorable. Or prime. All right. Another binomial, special type of binomial we will touch base with factoring is called the difference of cubes. The difference of cubes looks like this in general. Difference means subtraction. The difference of cubes in general always factors according to this pattern. This is how the difference between two cubes always factors. If you were to take the time and multiply this all back out and gather together like terms, you would discover that you would get back the a cubed minus b cubed. The sum of cubes. In general, this is what the sum of two cubes looks like. The sum of cubes factors in a very similar way that the difference of cubes factored. The only difference is the signs are moved around a little bit. This would factor in a plus b times a squared minus ab plus b squared. Notice the only difference between factoring the difference of cubes and the sum of cubes is the patterns are identical. The only difference is where the negative signs are. Here the minus signs in between a and b, and you have a plus sign between a squared and ab. Here you have a plus sign between a and b and a minus sign between a squared and ab. I always remember it this way. Whatever this sign is here is always the sign that is in the binomial factor. So you got a minus here, there's going to be a minus here. A plus here, you got a plus here. These signs are always going to be opposite. If you got a minus sign here, you're going to have a plus sign here. If you got a plus sign here, you're going to have a minus sign here. So you can see there's distinctive patterns here. All right, the last type is called a perfect square trinomial. If you have a trinomial that looks like this in general, a squared plus 2ab plus b squared. Ladies and gentlemen, any trinomial that looks like this, where the first and last terms are perfect squares and the middle term is twice the first term times the last term, this would factor in a plus b quantity squared. This is called a perfect square trinomial because it factors into the square of a binomial. In a similar note, if you have a perfect square trinomial that's like this, a squared minus 2 times a times b plus b squared, this would factor very similarly, but this would factor as a minus b quantity squared. And there you have it. These are the special form polynomials that are put under the microscope in section 6.4. Um, so notice the majority of these special types are binomials. I like to call this the binomial family. The difference of squares, sum of squares, difference of cubes, sum of cubes. These are how these all factor. And these are special types of trinomials called perfect square trinomials. I know it seems like a lot, ladies and gentlemen, but these are patterns that you just want to become somewhat familiar with. Just, kind of, look at these and try to fixate on these and put these in your mind, because these are useful patterns, not only for this course, but if you go onwards, a lot of you have to take intermediate algebra, math 120. You will revisit these special forms in your attempt to factor these types of constructs or these types of polynomials. So now that we know these special forms, let's dive right in and try to factor several examples that fit these special forms of polynomials. All right, first one here will be x squared minus 25. Off to the right side of my paper, I'm going to list the first several perfect squares. It's wise to at least see maybe the first 20 perfect squares so that you are more, let's say, experienced in determining whether you do have the difference of squares. So the first 20 perfect squares would be 1. If you square 1, you get 1. 2 squared is 4. 3 squared is 9. 4 squared, 4 times 4 is 16. 5 squared is 25. 6 squared, 6 times 6 is 36. 7 squared is 7 times 7 are 49. 8 squared is 8 times 8 are 64. 9 squared, 9 times 9, 81. And 10 squared, 10 times 10, 100. I'll continue to list over here. 11 squared, 11 times 11 is not 111. Actually, it's 121. 12 squared, 12 times 12 is 144. 13 squared, 169. 14 squared, 14 times 14 is 196. 15 squared, 15 times 15 is 225. 16 squared is 256. 17 squared is 289. 18 squared is 324. 19 squared is 361. Finally, 20 squared is 20 times 20 or 400. And so, ladies and gentlemen, I've listed the first 20 perfect squares. All these numbers to the right of the equal signs are called perfect squares. Obviously, this list goes on forever, as there are an infinite number of perfect squares. I've just listed the first 20. Now, that becomes useful when we're being asked to try to factor a binomial that is x squared minus 25. You can clearly see that 25 is a perfect square. Since 25 is in our list here, it's a perfect square of 5. Being the case, x squared minus 25 definitely is a binomial, which is the difference between two squares. And if you don't believe me, ladies and gentlemen, let me rewrite x squared minus 25 to further illustrate that fact. X squared minus 25 can be rewritten as x squared minus 5 squared. Below it, I'm going to put the pattern that we had established on the previous page. You can see that this definitely fits the mold as being the difference between two squares. And in general, we've seen on the previous page that the difference of squares always factors into the product of two conjugate binomials. And so, just following along this pattern here, x squared minus 25 will factor in a similar way, where our a is really an x and our b is really a 5. So it's just a matter of dropping an x in place of wherever you see a in these factors and dropping a 5 in wherever you see a b. So x squared minus 25 is going to factor into x plus 5 times x minus 5. And we're done. This is the correct factorization of this difference of squares, x squared minus 25. This is your answer. Let's try another one. How about a squared minus 64? Notice there's nothing we can factor out of both these terms. It is a binomial, and it turns out, after a little thought, that we do have the difference between squares again, as 64 is indeed a perfect square of the whole number 8. So a squared minus 64 can be rewritten as a squared minus 8 squared. Therefore, ladies and gentlemen, it can factor according to the difference of square pattern, which is right above here. This would therefore factor into a plus 8 times a minus 8, and we're done. This would be the correct factorization of a squared minus 64. Y squared minus 121. Again, after a little thought and inspection, we realize that we do have the difference between squares again, as 121 is a perfect square of 11. So y squared minus 121 is really equal to y squared minus 11 squared, which clearly indicates that we do have the difference between squares. So therefore, this will factor. And it will factor into y plus 11 times y minus 11. This is the correct factorization of y squared minus 121. Done with that one. All right, how about 4t squared plus 81? This is the binomial. Notice there is nothing we can factor out of both these terms. After a little thought, we realize that we have what is called not the difference of squares, but the sum of two squares. 4t squared is really the square of the monomial 2t. 81 is a perfect square of 9. But ladies and gentlemen, we established on the previous page that the sum of perfect squares can never be factored. And so therefore this binomial we say is non-factorable. All right, let's try another one. How about 25m squared minus 169? Here we have a binomial, and as it turns out, it is the difference between perfect squares. 25m squared is definitely the square of the binomial 5m. 169 is a perfect square of 13. 169 is a perfect square of 13. So therefore, 25m squared minus 169 factors into 5m plus 13 times 5m minus 13. That's how it factors. All right, how about 16 minus z squared? This is a binomial, and it is the difference between two squares, 16 being a perfect square of 4. So therefore, this binomial or difference of squares factors immediately into the conjugate binomials of 4 plus z times 4 minus z. And we're done. That would be the correct factorization of 16 minus z squared. Factoring c squared minus 256. 256 is in our list over here. It definitely is a perfect square of 16. So c squared minus 256 is indeed the difference between two squares. So, being the case, it will factor into the product of two conjugate binomials, namely c plus 16 times c minus 16. And we're done with factoring that difference of squares. Sometimes you may have to do more than one round of factoring, and that will become the case as we wrap up this chapter. Let's try to factor y to the fourth minus 81. Now this one here is going to require that we go a little bit further. Y to the fourth power really is the perfect square of y squared. If you square y squared, you get y to the fourth. And 81 is certainly in our list over here. 81 is a perfect square of 9. So ladies and gentlemen, you can see that we do have the difference between two squares. difference between two squares. So therefore, this would factor immediately into the product of two conjugate binomials. The first terms of which have to be y squared, because that's the first term that's being squared. And the last term is 9 that's being squared, so our conjugate binomial factors will be y squared plus 9 times y squared minus 9. Now we're going to find out, as we wrap this chapter up, that when we're being asked to factor a polynomial, it's understood that we completely factor our polynomials. Well, this is not completely factored. Although y squared plus 9, the first factor, is the sum of squares, which cannot be further factored down, we see that the second factor, y squared minus 9, is itself the difference between two squares. So it itself needs to be further factored down. And so, ladies and gentlemen, to completely factor y to the fourth minus 81, we must go further. So we put another equal sign. Y squared plus 9 just comes down since it's not further factorable. But y squared minus 9 further factors into the product of conjugate binomials, namely y plus 3 times y minus 3. So again, y squared minus 9 further factors into y plus 3 times y minus 3. And since none of these remaining factors can be further factored down, we say that this is the complete factorization of y to the fourth minus 81. All right, so that gives us a good workout on how to factor the sum and difference of squares. Now we're going to look at how to factor the sum and difference of maybe some perfect cubes. I'm just going to list the first several perfect cubes. I'm not going to go and list all 20 of them because the perfect cubes grow quite quickly, and I'm not going to ever, give you very large perfect cubes anyways in this course. But anyways, if you were to take 1 and cube it, 1 times 1 times 1, you would get 1. So 1 is a perfect cube of itself. 2 cubed, 2 times 2 times 2 is 8. 8 is a perfect cubed, we say, of 2. 3 cubed, 3 times 3 is 9, and 9 times another 3 is 27. 27 is a perfect cubed of 3. 4 cubed, 4 times 4 times 4. 4 times 4 is 16, times 4 is 64. 64 is a perfect cubed of 4. 5 cubed, 5 times 5 is 25, times another 5 is 125. So 125 is a perfect cubed of 5. 6 times 6 times 6, or 6 cubed, as it turns out, is going to be 30. 6 times 6 is 36, times another 6 is 216. That's a perfect cubed of 6. 7 cubed, 7 times 7 times 7. 7 times 7 is 49. And 49 times another 7 is going to be 343. So 343 is a perfect cubed of 7. And of course, this list goes on and on and on forever. I just listed the first 7 perfect cubes. That should be good enough for our work. All right, let's try to factor one like this. Let's try to factor y cubed plus 8. Here we have a binomial, ladies and gentlemen. There's nothing to factor out of both these terms. Notice that this is not the difference of two terms, but it's the sum of two terms. And it's not the sum of perfect squares, as y cubed is not a perfect square. But after a little thought, it appears to be maybe the sum of two cubes, not squares. Y cubed is obviously a perfect cube of y. And 8 is a perfect cubed of 2. 8, a perfect cubed of 2. So you can clearly see after rewriting y cubed plus 8 like this, you can see that we do have the sum of two cubes. Now the sum of two cubes can always be factored. I'm going to put the pattern above here that we've seen on the previous page to open up this section. When we do have the sum of two cubes, it always factors into the product of a binomial and a trinomial. So this would factor into a plus b in general times a squared minus a times b plus b squared. So in order to factor y cubed plus 8, all we have to do is follow along with this pattern here. Our a is really a y, and our b is really a 2. So wherever we in this pattern see an a, we replace the a with a y, and we replace a b with a 2. So let's just follow along with the pattern. We have a plus b, which is really to say y plus 2, times a squared, which is to say y squared. Remember, our a is really a y, minus a times b, so minus y times 2, or minus 2y, plus b squared. Our b is really a 2, so plus 2 squared at the end. Now you want to clean this up. Don't leave this looking this way. So this would simplify to y plus 2 times y squared minus 2y plus 2 times 2 at the end, or 2 squared should be reported as 4. And we're done. So ladies and gentlemen, this is the correct factorization of y cubed plus 8. If you were to take the time, and I'm not going to do so, but if you were to multiply this all out and gather together all your like terms, you would see that you would get back y cubed plus 8. I know it doesn't seem like it, but it would give you back y cubed plus 8 if you multiply this all out. So we just factored the sum of 2 cubes. All right, let's try another one here. Let's try to factor t cubed minus 1. Notice this is a binomial here, and it is not the difference of squares, but it turns out to be the difference of perfect cubes. T cubed is obviously a perfect cube of t, and 1 is a perfect cube of 1. So you can clearly see that we do have the difference between 2 cubes. That being the case, we're going to factor it according to the pattern of the difference of cubes. And I'll recite that pattern right here. So in general, when you have a cubed minus b cubed, the difference between cubes, it always factors into a minus b times a squared plus ab plus b squared. So that's how it always factors. So our a is really a t, our b is really a 1, and so that being the case, wherever we have an a in this pattern, we replace a with t, and we replace b with 1. So a minus b is same t minus 1 times a squared, or t squared, plus t times 1 plus 1 squared. And so we really have t minus 1 times t squared plus, now t times 1 is reported better as 1t or t, and 1 squared at the end is just 1. And there you go. That would be the correct factorization of this difference between 2 cubes. All right, z cubed plus 27 is a binomial, and upon further inspection we can see that it's really the sum of 2 cubes, because 27 is a perfect cube of 3. So since we do have the sum of cubes, we have to factor it as the sum of cubes. And to help us do that, I'm going to put the factorization of the sum of cubes below here so that we can see the pattern in general. And so, ladies and gentlemen, our a is really like a z for this pattern's sake, and our b is really like a 3. So wherever we see an a in this pattern, we replace it with a z. So a plus b is going to become really z plus 3. B is replaced with a 3. So here we go with our factorization. A plus b is really z plus 3 times z squared, because we're squaring a. Remember, a is really z. So that's z squared minus z times b. Our b term is a 3, so z times 3 is minus 3z plus 3 squared. Now, we should not leave this 3 squared as 3 squared. We should turn it into a 9. So therefore, To wrap this up, the factorization of z cubed plus 27 is really going to be z plus 3 times z squared minus 3z plus 9. And that's the correct factorization, ladies and gentlemen, of the sum of these two squares here. So in general, that's how we factor the sum or difference of perfect cubes. All right, just a couple more perfect square trinomials. Now, perfect square trinomials can be factored just by using the grouping method that I showed you in the last section for factoring difficult types of trinomials. But if you know the pattern for perfect square trinomials, sometimes when the numbers get really large, that can really help you save a lot of time as opposed to using the grouping method. For instance, suppose we're being asked to factor this trinomial 25y squared plus 30y plus 9. Now, ladies and gentlemen, if we look at this trinomial, we can see that the first term, 25y squared, is a perfect square of the monomial term 5y. And the last term, 9, is a perfect square of 3. And the middle term is twice the first term times the second term. So what I'm trying to say is this. This trinomial is the first term squared, the last term is squared, and the middle term is 2 times the first term times the last term. So this being the case, whenever you have a trinomial that looks like this, we call this a perfect square trinomial. And perfect square trinomials can always be factored. And according to the pattern we established in opening up this section, this perfect square trinomial would factor in general as a plus b quantity squared. Now, upon further inspection, we can see that our a term is really 5y. A is 5y. Our b is really a 3. So ladies and gentlemen, to factor this perfect square trinomial, we replace a with 5y plus, we replace b with 3. And we're done. So therefore, the correct factorization of this trinomial here, 25y squared plus 30y plus 9, is 5y plus 3 quantity squared. It's called a perfect square trinomial. Now, you could factor this using the grouping method, but you'd have to take 25 times 9, and that gives you like, I believe, 225. And trying to find two factors of 225 that add up to 30 could take a while. For that reason, recognizing that this trinomial is a perfect square trinomial and knowing how to factor a perfect square trinomial gets us there a little bit quicker in our ability to factor this trinomial. Let's try another one here. About 100x squared minus 140x plus 49. Notice there's nothing you can factor out of all three terms of this trinomial, and to factor it using the grouping method would be somewhat cumbersome because you'd have to take 100 times 49, which would give you 4,900. And it's kind of difficult to think of what two factors of 4,900 would be that would sum up to negative 140. Being the case, you might want to, ask yourself, might this be a perfect square trinomial? And after a little thought, you'll see that it is, because the first term really is the monomial 10x squared. The last term, 49, is clearly 7 squared. And the middle term is going to be minus 2 times the first term times the last term. This should be a 7 right here. So clearly, you can see that this trinomial is of the type of a squared minus 2 times a times b plus b squared. It is a perfect square trinomial, and we seem to open up the section that this would factor immediately into a minus b quantity squared. Now your A term here is really like a 10x. Your B term is really like a 7. So to factor this perfect square trinomial, all we have to do is replace A with 10x and replace B with 7. And we're done. This would be the correct factorization of 100x squared. Excuse me. This would be the correct factorization of 100x squared minus 140x plus 49. These are called perfect square trinomials. Again, you could factor this using grouping. 100 times 49 is 4,900. But it would take a while maybe to find two factors of 4,900 that add up to negative 140. So it's a little bit more efficient to recognize that this is a perfect square trinomial and to factor it in accordance to our pattern that we've seen earlier. All right, well, that concludes, ladies and gentlemen, section 6.4. The only way you're going to get good at factoring polynomials is by doing a whole bunch of practice. And, hopefully you are staying up with the homework, as it does afford you with practice. I may post some additional practice on Blackboard. Stay tuned with the email on that. And of course, doing the activities also affords you more practice. I'll try to write the solutions out to your activities from now on and post those on Blackboard. And of course, we all get 100% on our activities from here on out. That's the good news. Um, and so the only thing you have to submit to me, ladies and gentlemen, via email is going to be your textbook homework, which will be due during the week of the exam. Stay tuned on an email for more specific information with regards to that. In all likelihood, your exams that I will email to you, your exams will be multiple choice exams for the most part, and you'll have to email me back your answers to those exams. Um, but try to become somewhat efficient or proficient with factoring, because it is a critical skill you're going to need for a higher level math. If you do take intermediate algebra, they are going to expect that you do know how to factor some polynomials. And so do not take chapter 6 lightly, ladies and gentlemen. It's a critical chapter to be successful in higher level math. All right, talk to you later. Stay safe.